Okay, let's learn about Newton's laws. Now, Newton's laws are part of the forces topic, which for us comes into physics paper 2. Newton's laws are very important because with the question that we're going to look at today, you need to understand all of the 3 main laws. So we'll start off by going through them. Newton's first law says, or states, that a resultant force is needed to make something move. Okay, a resultant force is needed to make something move. So if we think about this, there's a box on a surface. It's not moving. It's 0. The resultant force is 0 because it's not moving. So if something is not moving, it has a 0 resultant force. If something is moving, so we take the same box again, but this time we push it with a force of 5 newtons, but friction slows it down by 2 newtons. Then overall, there's a force, a resultant force of 3 newtons to the right. So an object's only going to move if it has a resultant force acting on it. If there is no resultant force, it's not going to move. That's Newton's first law. Okay. Newton's second law says the larger the resultant force acting on an object, the more the object accelerates. And that tells us that force is proportional to acceleration. Okay. And we also have, as part of the second law, the interaction between the force and the mass and acceleration. So the second law also tells us a larger mass will accelerate less. If the same force is applied. Okay, and that brings us to force is equal to mass times acceleration. Okay, where force is measured in newtons, mass in kg, and acceleration is meters per second squared. Okay, so that is the 2 bits, the 2 aspects of Newton's second law. Okay, first law, nothing's going to move unless it has a resultant force acting on it. Second law says the larger the resultant force is, the faster or the more the object's going to move, the more it's going to accelerate. That makes sense, doesn't it? But also, if the object is larger, it will accelerate less. If it's smaller, it will accelerate more. Okay. Newton's third law. Now, the first and second law always kind of like link together, obviously, because to do the second law, you've got to work out the resultant force. Okay. The third one says when 2 objects interact, the forces they exert on each other are equal and opposite. Okay, so we have the example of, say we've got a brick wall here. And we've got person leaning against a brick wall. Let's put them at an angle. We've got a person leaning into the brick wall. Then the force with which the person is leaning is the same as the force of the wall opposing that, equal and opposite. Okay. The other common example is you have two ice skaters and they meet and then they push back from each other. They're going to move, they're going to push back with each other with the same amount of force. Okay, let's go straight into a question. Okay, we have here a person using a device called a jetpack. Water is forced downwards. Now, the important thing here is look at the words that the question is using. It's using the word downwards and upward force. We can use the same words in our response. Okay, so the diagram below shows a person using a device called jetpack. Water is forced downwards from the jetpack and produces an upward force on the person. So we have a downward force, which is this way, and we have an upward force, which is this way. Now think about Newton's first law. Look at question A. State the condition needed for the person to remain stationary. So for them not to move. Newton's first law says that you have to have a resultant force applied to an object in order for it to move. And in this question, it's saying that the person's not moving. They're in a position above this water, but they're not moving, but they're stationary, but they are above the water. So if they are not moving, it means that there isn't a resultant force, but there are two forces working on this person. The question tells us there's an upwards and a downward force. So if the person is not moving, then that means that the upward and downward forces are equal. Therefore, meaning that there is no overall force acting on them. Does that make sense? Okay. This one here. The person weighs 700 newtons and the jetpack weighs 140 newtons. Calculate the combined mass of the person and the jetpack. Now here, we use a different equation where weight is equal to mass times gravitational field strength, and weight is the force and it's measured in newtons. Okay. We've got the weight of the person in newtons and the weight of the jetpack. So combined, they have a weight of 840 newtons. We know what gravity is. We need to work out mass. Okay. So we substitute it in. 840 is equal to the mass times 10, because it tells us in the question to use 10 as our value for gravity. So 840 is m times mass times 10. If I divide both sides by 10, I'm going to get the mass to be 84. Okay, so we're bringing in that weight and mass and gravity as well. Increasing the upward force to 1850 newtons causes a person to accelerate. Okay, so we've got an upward force of 1850. Our downward force, we take it from the question above. The downward force is there because of the person and the jetpack's weight, which is 840. So the downward force is 840. And from here, we need to calculate the acceleration. So there's a few steps here. First of all, we need to work out the resultant force. Okay. And then we need to decide how we're going to go from our resultant force to our acceleration. Now, it's important that we recognize that we do have a value for mass also. All right. So here, what we're going to do is we need to work out the resultant force first, because it tells us that the person is moving. They're moving. So there must be a resultant force. So to work out the resultant force, we find the difference between the upward and the downward force. Just going to double check. (1010). Now this is our force in newtons. So we put this into our force is equal to the mass times acceleration. We're working out acceleration. We know the force is 1010. We know the mass is 84. And we know the acceleration is what we're trying to work out. Gives us an acceleration of 12.02, whatever. It's 12. Remember now the unit is standardized. It's always going to be meters per second squared if we're using this formula. Okay, so this question is really good because it brings in a lot of the things that we need to tie in when we're thinking about the first, second, and third laws.